Hi there, my name is Christopher Wurst. Welcome to the first video of Homework 4 for Material Energy Balance. This one's going over reactor dynamics. In this video we're doing part 1, which says derive the time-dependent material and energy balance questions of the CSTR described. Now, there is a example underneath here that says to illustrate how the CSTR can exhibit nonlinear dynamic behavior, we simulate the effect of a step change in the coolant temperature Tc in positive and negative directions. Table 2.3, which is shown below here, shows the parameters and nominal operating condition for the CSTR based on some equations for the exothermic, irreversible, first-order reaction A to B, which is a chemical reaction. The two-state variables of the ODEs are the concentration of A, Ca, and the reactor temperature T. The manipulated variable is the jacket water temperature Tc. So, to start, I'm going to first draw up a picture. Here, over here, it says, So we have a reactor here. And we have a cooling jacket filled with cold water to make sure that the reaction doesn't get overheated. So we know that there is flow coming in, flow coming out, as represented in the variables on the screen, as well as a few other things that control the temperature and the concentration of A. So the reactor is at some temperature T. There's flow in and out of the reactor at some given speed q. At temperature, the temperature in is given down on the screen, as well as the temperature of the coolant. And then, of course, the temperature of the coolant comes out here just to keep it cool. So we have a bunch of variables down here. I've already explained Q. I've already explained the temperature in, which is that what looks like pi, but that's a T. And C is the constant, and C is something else. Tc is on the right side is the temperature of the coolant jacket, and then Ca is what we're looking for, is the concentration of A in the reactor. So everything else, we've got volume, we've got the speed of the flow rate in and out, and the flow rate in and out are the same, so we're just going to refer to them as Q. We have our concentration of A coming in. We have our concentration of A in the reactor, which, because this is well mixed, means that the concentration of A going out of the reactor is equal to the concentration of A in the reactor. So we have Ca. We have we're given the density, which we'll use later. We have C, which is the heat capacity for the product in the reactor, as shown on your screen. We have the change in the in overall enthalpy of or the energy in the due to the reaction. We have the activation energy divided by R, which gives us the activation temperature about, or how much, the activation energy. We'll use that later for K, which is the rate constant. And then we have K naught. We have a variable UA, which when combined with some temperatures gives us the heat transfer from the reactor to the coolant. We already have our TC, and then we have our general temperature. So that's all the, this is all the variables that we need, and now we can start writing out what we need. So the question asks for two equations, one for the material, one for the energy. So we'll start with the material. So the change in moles is equal to the change in the concentration of A in the reactor times the volume. Over time, which is equal to the flow rate in multiplied by the change in concentration from Ca in, the concentration of A flowing in, and the concentration of A in the actual reactor itself, represented here, minus, because the concentration of A gets used up as the reaction goes on, minus the volume in the reactor over there, which is constant, times the rate constant of the reaction times the concentration of A. Now, the rate constant is equal to K naught, the rate constant naught, which is given in the example. Which is equal to multiplied by e to the power of the variable e divided by r divided by the temperature. And that goes up and down into the equation. So we have this here, and now we're just looking to get the change in concentration of A by itself. And we do that by simply dividing across. So we've got this divided by volume, and this divided by volume, and this volume will cancel out. So that means that all told, the change in the concentration of A in the reactor over time is equal to the rate constant, equal to the flow constant, Q, divided by the volume, multiplied by the difference in concentration of A from the flow in and the reactor, and that which is in the reactor, minus the rate constant times the concentration of A for how fast the reaction is going. Now that we have this is one thing that we need. Now we need the energy equation. So what is the energy? The total energy in the total change in the energy in the reactor is equal to, if you see C as the heat, it's the heat capacity, and then the change in temperature. So, and change in temperature is what we're looking for. So, if C is given by joules divided by grams times Kelvin, then we have volume times and density, that will give us grams. So, we've got density times volume times that heat capacity constant. So rho VC times the change in temperature over time. And this is what we're looking for. Now, all told, this is equal to the change in enthalpy in the reactor, as well as the heat transfer, or how much heat is being leached out of the reactor by the coolant. So we've got the enthalpy change. H in minus H out, the difference in enthalpy. And then minus as well, that variable here, UA, times not Tn, the difference in the temperature in the reactor and the temperature in the coolant. So that's actually T, general T, minus TC, temperature in the coolant. So we have this, but you notice we don't have variables, or given variables, for the enthalpy of the reactor, of that flowing in, minus the enthalpy of that flowing out. So we need to find these two. So, and I'm starting to get a little bit low, but I'll do my best to crouch. So this doesn't change, so these just go down. And then that'll go down later. Now, H in is the enthalpy of that flowing in, so we've got Q, the flow rate in, and we're going to be multiplying that by density. And to C, for because the flow rate in is effectively the volume for this, so this functions the same as the heat capacity, and it's the heat capacity for the flow rate in. And then we need the difference in temperature between the flow in and the flow and the product in the reactor. Now we need H out, which is equal to the negative delta HR, the heat, the change in heat of the reaction. So negative delta HR multiplied by the volume, and we need volume again, times the rate constant, times the concentration of A, because again, a reaction is going on here. And then the heat transfer just comes out. So I'm not going to be able to crouch anymore. So I'm going to copy this up here. So I'm going to erase my variable list. All right, so now that this has been copied, I'll get this out of the way. I'll also get this out of the way, because we don't need it anymore. And now that we have all of that, and we have all variables that we will know, we can just get the change of temperature over time on its own. So the change in temperature over time is equal to all of this divided by the heat capacity. So we've got Again, like over here, the flow rate divided by the volume, because density and that heat constant cancel out over here and here. Multiplied by the temperature, the difference in the temperature in and the temperature in the reactor, minus change in heat from the reaction flow rate, the reaction constant, and the concentration of A in the reactor divided by the density and that heat constant, and then minus the heat capacity divided by, or heat transfer divided by the heat capacity. So with that, we have equations for our two changes, and in the next part we can take a look at and model what will happen if we take steps in changing the heat of TC, the coolant heat, or changing the coolant heat. That's all we'll be doing. So with that, hope you have a wonderful day.